Okay, today we close our discussion on ultrafast dynamics in semiconductor nanoparticles. So far, we have been talking about excitons and how they evolve. We have talked about exciton trapping, we have talked about the ultra short and ultra long time constants, and we have seen an elegant example where a rather complicated decay has been handled and useful time constants and rate constants have been extracted from there. Today, we move on to another phenomenon that is very peculiar and is observed in nanoparticles, and that is of multi-excitons. As we have discussed already, and it is common knowledge nowadays that nanoparticles have bands like in bulk, but then within the bands they also have these discrete energy levels, and we have talked about how they are named. This is sort of NL kind of nomenclature. This one is it is easier to go by L. S stands for the angular momentum of the exciton. If it is 0, then the level is designated S. If it is 1, then it is designated P. If it is 2, then it is designated D, and so on and so forth. And the reason why the lower ones are designated H is that after excitation, these lower energy levels are occupied by holes and higher ones are occupied by electrons. And the one that is there, that is N, that denotes the number of levels of particular kind of angular momentum. For example, this is 1s because this is the first level with angular momentum 0, 1p first level with angular momentum 1, and so on and so forth. And this review, by the way, by V.I. Klimov is very instructive. What we will do today is that we will really gloss over several papers. It is not possible to discuss the vast body of literature that exists in this field, but it is important that we individually actually read those papers cover to cover, then only we will understand the field. Right. So, we have also said that the absorption spectrum in semiconductor nanocrystals shows several features due to different kinds of transitions. The lowest energy one is called the band edge transition, because it involves the energy levels at the edge of the conduction and the valence bands. However, you can have a promotion from a lower level. So, after promotion the hole can be left in a lower level and the electron can be in a higher level, and so on and so forth. One thing that may be noted is this. See, we have drawn this arrow here from 1s H to 1s E. We have not drawn a line from here. Well, we actually have drawn from here to here as well, but the point I am trying to make is that selection rules do hold here as well. And if you do a good experiment, if you have uniform nanoparticles and if the absorption spectrum is recorded properly, then one can see features like this, which are very easy to miss, because in any case there is a scattering background that is there. But different excitations can take place at energies higher than the band gap as well. So, what we talk about today really is what happens when excitation is performed at energies greater than band gap. And in this discussion, it is conventional to write the x axis as E by E g. How much above band, by what factor above band gap are we exciting? That is what is typically used, and results are also discussed in these terms. So, that is what we are going to do. So, you can say this is the band gap. So, this is E g, this is 2 E g, 3 E g, 4 E g, and so on and so forth. What happens is, for that kind of an excitation, the electron reaches a higher energy level, and the hole in the general case would also reside at a lower level. Hole residing at a lower level, remember, means that electron has been promoted from a lower level, and so energy is more. So, to start with, what we produce is called a hot exciton. A hot exciton means an exciton that has more energy than the band gap. A cooled exciton has energy equal to band gap. So, in this phenomenal work by Beard and co-workers, what they have done is that they have tried to explain what happens when hot excitons are formed. In other words, they have studied hot exciton dynamics. And a very interesting thing that happens if one uses an excitation energy of more than 2 e.g. is that when this electron comes down to 1 s.e. and the hole floats to 1 s.h., the energy that is involved can be utilized to cause another electron hole separation to lead to what is called a biexciton. So, biexciton, remember, is within a single nanoparticle. Within a single nanoparticle, you have 2 electron hole pairs instead of 1. And when one wants to study this phenomenon, one has to be very careful about something. If you use too much of pump fluence, then also you can actually generate biexcitons by the excitation itself, because every nanocrystal is subjected to a lot of photons. One photon will cause only one transition, but if a single nanoparticle is bombarded with millions of photons, then it is possible to have more than one electron hole pair formation in a single nanoparticle directly, even if one uses pump energy of not more than 2 e.g. That is a different ball game altogether. In fact, there has been a lot of study in that as well. We are not getting into that for the paucity of time. So, what they also proposed is that after the biexciton formation, there is an Auger recombination which leads to formation of single exciton. So, how would this show up and what is the time scale involved? It would show up in transient absorption data like this. Now, these transient absorption data are again we have encountered tail matching again and again in this course. These transient absorption data are also tail matched at long times. Well, tail is at long times. So, that is I am saying tail matching at long times is sort of saying the same thing twice. But when they are tail matched, what one sees is if you look at the transient absorption decays, this transient absorption, not ground state bleach. Ground state bleach is once again a little different story. So, what one sees is as you go from 1.9 e.g. to say 4.66 e.g. excitation energy, then we see the emergence of an ultrafast component that gets over by 200 or 300 picosecond. That is the time involved in cooling of hot excitons, formation of biexciton, so on and so forth. But again, this is rather complicated dynamics, because it is not as if hot electrons are formed and then they cool down and form single excitons. Hot excitons are formed and then they cool down to form single excitons. The intermediacy of biexciton is always there. So, to understand that, one needs to analyze the data very, very carefully, and in this seminal paper of Nozick comes handy. So, what Nozick had discussed in this paper, this review, annual review of physical chemistry published in 2001, is what happens after what is called impact ionization. Impact ionization means what we have said earlier, formation of a hot exciton. And he said the first step is always biexciton generation. Taking a clue from there, Klimov and Scheller and Klimov did a more elaborate study few years later, and these are all very interesting papers, and these are really papers that have pushed the frontier. This is absolutely new. Novelty is one thing that is not in question in the papers that we discussed today. So, what they said is that okay, you have impact ionization and then you have Auger recombination, and then you can have formation of exciton like this. So, their model, the model that they used was immediately following photoexcitation, and what they did is they did photoexcitation at more than thrice band gap to ensure the formation of hot excitons. So, this is a model that you have hot excitons that are formed, and of course, the reality is not this homogeneous also, because do not forget we are working with femtosecond pulse, there is always a width, there is always heterogeneity. So, whatever we talk about here is really an idealized situation, and a manifestation of that will also show up in a result that we are going to see in a couple of slides. So, what they said is that 50% of this population undergoes impact ionization and formation of biexciton, remaining 50% undergo cooling. Cooling means the energy is given to the lattice, no further exciton formation is there. And then these biexcitons also undergo Auger recombination and cool down. This is the model they use to fit their data. We are not going into fitting of the data as such, because if we do, then to discuss this one paper again we are going to need 3 modules like we did last time. And now we are almost at the end of the course. Everybody is sufficiently familiar with the phenomena. So, we should be able to read this and understand ourselves, but it is time consuming, and I strongly encourage everybody to read this. All right. Now, while doing experiments like this, a couple of things need to be kept in mind. First of all, what we discussed already, we should use a low pump fluence, low intensity of pump light. So, what happens in ground state bleach is that you see a rise time in ground state bleach. So, rise time in ground state bleach is something that we may not expect at first thought. Why would there be a ground state bleach? You perform an excitation, population in the ground state gets depleted. So, the bleach is supposed to be instantaneous and then it recovers, that is associated with the decay. When can there be a rise time in a ground state bleach? When post excitation further depletion of the ground state population takes place, and that is what is happening here, is not it? While formation of biexciton, when the biexciton is formed, there is generation of another electron hole pair, and this another electron hole pair means that comes at the cost of excited state population, unexcited. So, if you think of how many unexcited nanoparticles are there, that number would go down. That is why one sees a rise in ground state bleach. And if I may digress a little bit, this is a phenomenon that is once again definitely not expected in molecules. We have talked a lot about molecules. In molecules, one does not expect it, but even in molecules, this can be seen, and it can be seen in something that has attracted a lot of contemporary interest. I am digressing from nanoparticles for a moment. I am talking about molecules now. Recently, there has been lot of interest in what is called singlet fission. Singlet fission means, okay, we have this S0 state, we have S1 state, we have S2, S3, whatever. We perform excitation to a higher singlet state, and this is something that we have seen already when we talked about Tahara's work. There we could actually see the emission from S2 state in ultrafast time scales. Singlet fission means, in case the energy of a triplet state is approximately half of the energy of some excited singlet state. Of course, I am talking about relative energies here. In case this happens, then this molecule can undergo what is called singlet fission. Means there can be further excitation to the triplet state. Okay. This will cool down, right, but while cooling down, that energy can be utilized by another molecule to get excited to triplet state, and in this molecule intersystem crossing would take place. In another molecule, the triplet state would get populated, right. So, you start with a situation like this. If I draw simply, this is your ground state configuration. This is excitation to some singlet state, which has energy that is double that of your triplet state, and then what you have is you take another molecule which is in ground state, this combination becomes something like this. Even in this case, one can see a rise in ground state bleach. I missed out on this while talking about molecules. So, I thought that since there is a very similar situation in materials, it is a good idea to just at least mention it once, right. But now, let us come back to the topic that we were discussing. What we have learned so far is that one can generate a hot exciton by promotion of the electron to a higher energy state, and when the hole is in a lower level per se, that hot electron cooling can generate biexciton, and then the biexciton can undergo auxiliary recombination to form regular excitons. And this would show up in a fast decay in the transient absorption when pumped at high energies. When I say energy, I basically mean when pumped at more at shorter wavelengths. I am not talking about pump fluence. Let us not confuse pump energy and pump fluence here. When excitation is performed at lower wavelengths, higher energies, then this phenomenon can be seen. That is when you see a fast decay in the transient absorption. That is when you see perhaps a rise time in the ground state bleach. At lower wavelengths, this observation is not there. So, the question one can ask at this point is, so what? This happens, great. So, what is the need of getting excited about this? Well, this multi-exciton generation actually has a rather elegant application, and that application is I am going to excite using one photon, and I am going to generate not one exciton, but several excitons. And in fact, that is what was shown by Klimov and co-workers in this nanolators paper that has really made an impact in the field. The title itself is such that you have to read the paper if you read the title. 7 excitons at the cost of 1, redefining the limits for conversion efficiency of photons into charge carrier. Okay, what use is it? Why should I get excited if I can produce more exciton per photon? Well, I should get excited because one very major application of semiconductor nanoparticles is in solar cells, light harvesting. So, the idea is that your solar cell should be able to absorb the light from sun, and it should be able to generate charge carriers. So, more excitons means we are going to get eventually more charge carriers. In the ideal case scenario, from each electron we should get an electron and we should get a hole. So, if it is possible to harvest the blue part of solar energy spectrum, and then if it is possible to generate more charge carriers per photon, per blue photon, I am saying blue in a very qualitative manner here, all I mean is higher energy. Or if it is possible to generate not 2, but 3 or 4, as they have shown here, they have generated 7 excitons. So, if I can generate 7 pairs of charge carriers, then it is great. So, that is why this is a rather important problem. But how did these people know that they have generated 7 excitons at the cost of 1? That is what we are going to discuss in the next module.